A 2 kilogram mass is oscillating at the end of a spring with a period of 2 seconds, and in a previous video, we found that the equation describing this motion was x of t equals 10 cosine of pi times t. In this problem, we're asked to find an equation for the velocity and acceleration of the mass as a function of time and graph those. In order to do so, we need to understand the relationship between position, velocity, and acceleration, and we need to know how to graph sinusoidal functions. The function which describes the velocity of an oscillating object is negative a, which is the amplitude, times omega, which is the angular frequency, times sine of omega t. This expression is derived by taking the derivative of the position function. Plugging in the numbers for the amplitude and angular frequency for our mass, we see that the velocity is equal to negative 10 pi times sine of pi t. We graph this function here, and we see that at time t equals 0, the mass starts from rest, and then as it's released, its velocity oscillates between negative 10 pi centimeters per second and 10 pi centimeters per second. The function which describes the acceleration of an oscillating object is equal to negative a, which is the amplitude, times omega squared, which is angular frequency squared, times cosine of omega t. This expression is derived by taking the derivative of our velocity function. Plugging in the numbers for our specific mass, we see that the acceleration as a function of time is equal to negative 10 pi squared times cosine of pi t. We graph that function here, and we see that at time t equals 0, the acceleration is negative 10 pi squared centimeters per second squared, and oscillates between this value and the value of 10 pi squared centimeters per second squared.